Of course, okay, sorry, I just click continue on the recording. Of course, the Clausius relation can be written as an inequality, so that the second law of thermodynamics is then encoded in this object here that is called the irreversible entropy production. And the second law tells us that the irreversible entropy production has to be greater or equal than 0. Of course, if the process is a reversible one, it goes through all equilibrium states. We have the Clausius equality, and this irreversible entropy production is equal to 0. So the irreversible entropy production is entropy that is produced in the system and accounts for the irreversibility of the process. Now, one can rewrite this expression in, let's say, more general terms, in the sense that one can rewrite the previous expression in a differential form, where here there is now the rate of change of the entropy, and on the right hand side there are now the entropy flux rate, which can be identified in the previous example with the heat flux rate, and an entropy production rate. Again, the second law of thermodynamics for non-equilibrium thermodynamics is encoded in the irreversible entropy production rate being greater or equal than 0. This is a bit more general than the standard formulation of thermodynamics, because it takes into account irreversible processes, which thermodynamics, equilibrium thermodynamics does not. And is also what characterizes the so-called stochastic thermodynamics, in which this irreversible entropy production being greater or equal than 0 is just an expectation value over all possible stochastic trajectory of your system. So essentially, this relation shows also the probabilistic nature of the second law. Now, what I'm interested in today in this talk is to try to answer to the following question. How do we define the quantum entropy production for continuously monitored quantum systems? Now, the first part of this question is very general, it's a research field by its own. How do we define the quantum entropy production? And for the people that are interested in this topic, I would like to suggest this very recent reference, well, this recent reference that was very recently accepted in a review of modern physics by Gabriel Landi and Mauro Paternostro, which are also the two of the co-authors of the work that I will discuss about in this talk. Now, the question that I'm posing is a bit more specific. So how do we define the quantum entropy production for continuously monitored quantum system? And an example of a continuously monitored quantum system, which most of you are probably very well familiar, is the one that I'm depicting in this picture here. That is the case of a nanoparticle levitated in an optical cavity, so it's an optomechanical system. And in this example, you see you have the mechanical mode B, you have your cavity mode A, then the cavity is pumped by a laser, and what is measured is the field that is leaking out of the cavity, for example, with an homodyne scheme here. Now, why is it interesting to ask how do we define the reversible entropy production for system of this kind? Well, the answer is that in the literature, this problem has been tackled in some way, but with some shortcomings. In particular, the usual way in which the reversible entropy production for quantum system, even without the measurement, is defined is by identifying the entropy fluxes with heat fluxes to a thermal environment. So that in this way, you can have this object phi here, the rate of entropy, you know, because you can assume that the entropy is the von Neumann entropy of the quantum state, and then you can, by subtracting, you can define your irreversible entropy production and the second law of thermodynamics. However, look at this optomechanical system. What is the thermal bath here? Well, for sure, there will be a thermal bath of phonons interacting with the center of mass degree of freedom of your particle, but there is also another thermal bath here that is given by the leaking output field. However, for an optical field at room temperature, you know that the occupation number is essentially 0. So this optical mode here plays the role of a zero temperature thermal bath. And when T's go to zero, of course, Q over T start to be problematic, physically speaking. It's a divergence, it's a singularity. So this first approach is not particularly useful whenever you don't want to have a heat bath that is interacting with your system. Again, whenever here also the phonon bath is not in a thermal equilibrium, again, you are outside of the region in which you can apply this kind of reasoning. The other way in which the entropy production has been defined in the literature, in particular, it can be defined in terms of the correlation between the environment and the system and the correlation, the changes in the environment itself. But even if I will kind of use this way in a moment, it has to be shown that also it has to be noted that also this way of defining entropy production has some shortcomings. And again, if you take this example here, this paradigmatic example, you can see that you don't have the control over the whole environment, first of all, and this is common any time that we do experiments in quantum mechanics. We don't control the whole environment. So in particular, the correlation between system environment and the changes in the environment, and even more when you have continuous measurement, because here there is a detector that you don't want to describe microscopically. Okay, so this is more or less the motivations why we started to look into this. And now the plan of my talk is the following. I will first of all introduce a very recent collisional model picture of thermodynamics. This will allow me to connect thermodynamical quantities with informational quantities and also discuss some interesting things like informational steady states. If I will be not too slow, I will also show you a couple of examples of how to apply this framework for qubits, but then I will pass to the case of Gaussian quantum system. And in the case of Gaussian quantum system, I will confront this collisional model picture with the semi-classical picture that we have worked on essentially in 2019. And finally, I will conclude with very rapidly with, again, sort of an experimental assessment of entropy production that has been performed in collaboration with the group of Professor Albert Lisser in Copenhagen. And here you can see the references for the different part of the talk. As I said before, we are also going to put on the archive very soon a work in which we use the collisional model picture for Gaussian quantum states. So let me now start with the first part. And so here I will try to give you some, well, the basics of the collisional model framework for thermodynamics that we have developed. And then I will discuss both informational steady state and the second law of thermodynamics for continuously monitored system in this framework. So first of all, what is a collisional model? Well, as the name says, is a model in which you essentially model the interaction between the system and the environment with collision, via collision. So essentially, you model your environment as an ensemble of identically prepared and independent ancilla, and then you discretize time so that at each time step, your system, here X, will interact with one of the ancilla, and then the ancilla will go away, and in principle, you can measure it, but I will come to this in a moment. So essentially, is the collisional framework is a framework in which you have just a simple unitary interaction between your system and the ancilla, one at each time. Collisional models are very general. In the infinitesimal time limit, they can recover the standard master equation for open quantum systems. And in particular, they are very, let's say, elegant description of, for example, the input-output formalism in quantum optics and quantum optomechanics. Here there is a sketch of this when you have a cavity and you have a system inside that can be the cavity mode or even an optomechanical system, and you describe the open dynamics with the input-output formalism, you are essentially doing a sort of collisional model. There are the input noise that are going in at each time and output mode that are coming out, that are essentially these ancilla that are interacting and then going out. So having said that, the mathematical description is very simple. At each time step, you have a unitary interaction between the system and the ancilla, and the dynamics of the system alone is recovered by just tracing out the ancilla in the usual way. And this gives rise to a Markovian open system dynamics. Now, a further ingredient that I need here, apart from the usual, again, collisional model picture, is the continuous monitoring, so the measuring of the system. And here I will assume that the system is measured in an indirect way, which is what you usually do in the laboratory. You measure here the output field. You don't measure the system inside of the cavity directly, because otherwise you should break the cavity. And so here I will assume that after every interaction, the ancilla gets measured. So essentially in a circuit picture, you have that the system is interacting at each time step with a different ancilla. And after the interaction, the ancilla are measured. And you get here a streak of outcomes, Z1, Z2, Z3, and so on and so forth. And the indirect monitoring of the ancilla is done in general via POVM acting on the ancilla state after the interaction. Okay. Now, of course, once you have this streak of outcomes that I will indicate with this Greek Z letter, you can find easily the probability of this record, and this is given just by tracing over all the systems the evolution. And you can, at this point, define what I will call a conditional state. So by conditional state, here I will mean the state of the system at time t conditioned on a particular set of outcomes until that time. And this can be easily defined in the following way. So you just take the trace over the ancilla of the evolution and you normalize with the probability of the outcomes. Another state that will be relevant in the discussion is what I will call an unconditional state, where the unconditional state is just given by the average over all possible histories of records of the conditional one. And this is essentially what we will get by solving the usual master equation for an open quantum system, the unconditional one. The conditional one is what you usually get by solving the stochastic master equation, in which you are conditioning on the outcome of the continuous monitoring. Okay. This is not relevant for what we are discussing here. I mean, you can always define the evolution in terms of the CP non-trace preserving map in a sort of, if you want, Markovian fashion, just that these are not normalized. Okay. At this point, we can finally start to speak about information, and afterwards I will connect it with thermodynamics. So for what regard the unconditional state, the information content of the unconditional state is, as usual, captured by the von Neumann entropy. In the case of the conditional one, instead, I will use here what is called the quantum classical information, that is written like this, but is not the quantum conditional entropy. The quantum conditional entropy can also be negative. This object here is not, and it's the average over all possible measurement records of the von Neumann entropy of the conditional state. And this captures the information in the conditional dynamics. These two quantities together, if we take the difference, they give what is called the Holevo information or Holevo quantity. And this quantity essentially tells us how much information we obtain by monitoring the system, as it is easy to see by the definition, or if you want, even by this rewriting, in which you have the average over the outcomes of a distance that is a relative entropy between the conditional and unconditional state. And this quantity is always greater or equal than 0. So this will be our measure of the information that is acquired by measuring the system. And this is a measure of an integral information, in the sense that it takes into account all the outcomes of all previous measurement previous to time t. We can also define something that gives us an idea of the information that we acquire at each collision, independently of the previous outcomes. And this quantity is the Holevo conditional information. Now, don't mind the first line. Let's just look at the second line that gives us the expression for this Holevo conditional information, because the second line has a very clear physical meaning. So here you see that in the first term, what is entering here is essentially the state at time t conditioned on the outcome apart from the last one. So essentially, by taking the difference between these two objects, we are comparing the two following dynamics. At first, the first dynamic is the following one, is the one in which we evolve the state from time t minus 1 to time t without taking into account the last measurement. So essentially, you are conditioning the system until time t minus 1, but in the last step, you are not taking into account the condition. You are just going on with the unconditional dynamics in the last step. And this is compared to the dynamics given by this transformation here, in which instead you are going from time t minus 1 to time t, conditioning also on the last outcome. So it's clear that this difference essentially encodes how much information you are getting by doing the last measurements against the situation in which you don't do just the last measurement. Okay, now why I'm introducing all this quantity? Well, the first reason is that using the Holevo conditional information, we can rewrite the information rate, which takes into account how the total information that we are acquiring changes in time, because it's just the rate of the Holevo quantity. And we can rewrite this information rate as the difference between our Holevo conditional quantity and something else that will take into account dissipation. So they will take into account the loss of the fact that you are losing information because you are interacting with an open system. And in particular, is relevant that this quantity is indeed greater or equal than 0. This is a sort of a balance equation. It's telling us that what is determining how the information about the system is changing in time is due to, in part, the information that we are acquiring at each collision, and on the other side, the information that we are losing because the system is open to the environment. And this allows us also to define the first important concept that we have found in our work, that is the one of informational steady state. Now, the system that you are considering can in general reach a steady state even when it is continuously monitored. And at the steady state, the Holevo information will no longer change, because once you are at the steady state, no matter how many other measurements you are doing, the knowledge that you have acquired till that point will not change. This means simply that the rate of the Holevo quantity is equal to 0. However, this doesn't imply that G and L are equal to 0. It can be, you can have cases in which they are both 0, but you can also have cases in which they are equal to each other. And in the case in which they are equal to each other and different from 0, we call it an informational steady state. As an informational steady state means that in order to maintain this steady state, you need to continue monitoring the system. If you stop monitoring the system, then the steady state will start to change. So it's a steady state in which there is a strict balance between information that you are gaining and what you are losing to the open environment, and this balance has to be maintained. When I will speak about Gaussian system, I will come back to this, and there maybe it will be even more clear what I actually mean. Of course, if you have questions, stop me at any moment. Okay, now, having spoke about the information, let's connect it with thermodynamics finally. And first of all, let me recap very briefly what is known for what concerns the unconditional dynamics. Now, with this delta sigma u, now I will call like this the reversible entropy production rate for the unconditional dynamics. And as before, this is just written as the variation of the entropy plus, and the sign is because this is the rate of entropy from the system to the ancilla, the entropy flux rate. Remember that this entropy flux rate, in the case in which the ancilla are preparing a thermal state, is just the rate of heat flux from the system to the ancilla. Then, how do we define this irreversible entropy production? For the unconditional state, for the unconditional dynamics, this has been done in several works. Here there are some key references. And essentially, the reversible entropy production rate can be defined as the sum between the mutual information between the state of the system and the state of the ancilla after the collision, plus the change in the state of the ancilla. This is just the relative entropy between the state of the ancilla after and before the collision. And this quantity, in accordance with the usual second law, is greater or equal than 0. And in principle, it has also a very nice physical interpretation. This tells you that in the unconditional dynamics, the irreversibility of the thermodynamical process from the point of view of the system is related to the fact that in tracing out the ancilla, you are losing the possibility to retrieve the correlation between system and ancilla and the changes in the ancilla state. So it's very elegant interpretation of this. But for what I need it, actually, I just need this expression in order to obtain finally the expression also for the entropy flux rate. And the entropy flux rate can be written in this very compact form. Okay, now having this, I can finally go to the conditional dynamics, so to the case in which we have some measurement, and see what happens to the law of thermodynamics there. So first of all, we rewrite the first expression here in its trivial generalization. So instead of having the von Neumann entropy here, now we'll have the quantum classical information. And this gives me an expression for the reversible entropy production in the conditional case. Now, how do we define explicitly this object? Well, in order to define this object, we start from the entropy flux rate, because the entropy flux rate can be generalized in a trivial manner. So we start from this expression that we have here on the left, and we generalize it by just substituting to the von Neumann entropy the quantum classical information, and here taking the average over the outcome at time t of the relative entropy for the state of the ancilla. Now, this can be written in a compact form like this, which is very similar to the previous one. However, they are not in general the same object. And they are not in general the same object because their measurement can cause a back action on the state of the ancilla. So the state of the ancilla, this rho tilde here, in general, is not equal to rho y prime. Is not general to is not equal to just the state of the ancilla after the measurement. However, in the following, I will consider that my measurement are such that this condition is satisfied, and you will see that in the Gaussian case, this can be satisfied without any loss of generality. For general system, this is not the case, so you are assuming somehow some particular form of the interaction. But let me work with this assumption here. So I will work with this assumption. That means that the conditional and unconditional entropy flux rate are essentially the same. So given this, I can finally obtain my form of the reversible entropy production rate. And this is given by the unconditional entropy production rate minus the information rate that we defined before. So you see that this relation, first of all, is connecting thermodynamical quantities with informational quantities, and is telling us that in general, well, it's telling us several things, actually. First of all, it can be shown that this irreversible entropy production is greater or equal than 0. And again, this is still the second law of thermodynamics. Actually, this is greater or equal than this delta I, if you want. Moreover, there are some facts that are relevant here that are that at the informational steady state, the entropy production rate of the conditional dynamics are the same, because if you remember at the steady state, this delta I, this information rate is equal to 0. One can also integrate this expression to obtain the total entropy production, and the total entropy production is equal to the unconditional one minus this positive quantity. So these tell us that the conditional dynamics is always more reversible than the unconditional one. And finally, the difference between the unconditional and the conditional is bounded by the integral of the differential information gain, our Holevo conditional quantity, so how much information we gain at each collision. Now, what I've shown until now is, again, a very general framework. There is a connection between informational quantities and thermodynamical quantities. And now I would like to show you some application of these, which possibly will make everything a bit also more clear. So let me go fast through the following slide, because these are just very simple qubit cases. And here I want just to show you when an informational steady state is formed or not, plus remark what we just considered in the framework. So the first example is the easiest one, is a qubit system interacting with qubit ancillas. And the ancilla are all prepared initially in a thermal state, diagonal in the computational basis. The interaction between the two is a swap unitary, and the ancilla is measured in the computational basis. Now, what we get if we apply our formalism is shown by these figures. The first one shows you that the quantum classical information is smaller than the von Neumann entropy of the unconditional dynamics. The second figure instead shows all the informational quantities. So we have the information rate, that is the blue curve, and you see that the information gain goes consistently to 0 at late time. The system is reaching a steady state. However, also the differential information gain and the loss term are going to 0. This tells us that here there is no informational steady state. The steady state that is reached by the dynamics is the same if you consider the conditional or unconditional dynamics in this case. And finally, in the last figure, you can see the integrated, so the total entropy production. And you see that the entropy production in the conditional case, the orange curve, is, apart from asymptotically, is always always smaller than the unconditional entropy production. Again, this means that measuring the ancilla, so a completely non-invasive measurement for what regards the system, renders the dynamics of the system more reversible. Again, this makes sense from the informational point of view, because you are acquiring information on the system. So in principle, you are making the whole process more reversible. A more interesting case that we could see for qubits is the following. Here I have a qubit that is interacting with a composite ancilla, where the ancilla is composed by 2 qubits, each ancilla, and the system interacts first with ancilla 1 and second with ancilla 2 sequentially. Ancilla 1 is again in a thermal state and is the one that will be measured in the computational basis. Ancilla 2 will not be measured and is prepared in a state with some coherence in the computational basis. Now, this is a way more realistic example than the previous one, because this is usually what happens in a laboratory. When you do a measurement on the outward mode of the cavity, for example, in optomechanical experiment, you are measuring just part of the environment. You are not measuring all of it. And this here is encoded in the fact that here there are 2 components of the ancilla, and only the first one is actually measured. So in this case, the dynamics is a bit nicer than before. And here I want just to show you that in this case, there is an informational steady state. The system reaches an informational steady state, and indeed this is shown by the fact that this information rate goes to 0 asymptotically, but the information gain and information loss, they instead go to a constant value. So this is the case in which we have an informational steady state, and in this case, if you were to stop measuring the system at late time, then you would lose your information steady state, and the state of the system will start to go back towards the steady state of the unconditional dynamics. Okay, as I said, here I wanted to go pretty fast, because now I would like to focus a bit on Gaussian quantum systems, which are very relevant for what concern quantum optics and quantum optomechanics, and they are often encountered in the laboratories. Now, at the formal level, a Gaussian quantum system is essentially described, well, is a system for which the Hamiltonian is at most quadratic in the quadrature. And here we use this notation in which I'm putting the quadrature of all my modes. So I'm considering n modes, and all the modes quadrature are in a vector ordered in the following way. So I have position, momentum, and so on and so forth, where these position momentum are just canonically conjugated quantum operators. So the Hamiltonian, as I said, has to be at most quadratic in the quadratures, and when you consider an open system, the Lindblad operator have to be at most linear. This guarantees that an initial Gaussian state, so a state for which the Wigner function is Gaussian, will remain Gaussian. And this is exactly what happens in most of quantum optics, quantum optomechanics experiment. Indeed, if you look in the literature, generating non-Gaussianity is not a trivial task sometimes. Some other times you don't want to generate them, because working with Gaussian state is way more simpler than having non-Gaussian ones. So, having said that, a Gaussian system can be completely described, instead of using the density matrix, by the Wigner function in phase space. And the Wigner function for Gaussian state will be just a multivariate Gaussian in phase space. Moreover, given the fact that the Wigner function is a Gaussian, in order to characterize completely the dynamic of the system, I don't even know I don't even need to know to have the Wigner function to start with. I just need the first and second moment of the distribution, because then they completely characterize the Gaussian. So essentially, the dynamics is completely determined by the dynamics of the first momenta, the expectation value of the quadrature, and the so-called covariance matrix that here we call sigma from now on. Okay, now how the dynamics of a Gaussian system actually looks in terms of these first and second momenta? Well, if you are considering an open quantum system in which you are not monitoring the system, the dynamics is described by the two equations here in the green box. So we have an equation for the first momenta, and then an equation for the covariance matrix, where A and D are the drift and diffusion matrices, respectively. However, whenever you are actually measuring the system and are conditioning the system on the outcome of the continuous monitoring, think, for example, when you do a continuous homodynamic detection on the output field from a cavity, then the first equation becomes a stochastic differential equation, and here there is a stochastic term where dW are just binary noises, and these matrices gamma and C depend on the kind of measurement that you are doing on the system. And the second equation becomes a nonlinear differential equation, because the new term that you are going to add will be quadratic in the covariance matrix. However, Gaussian systems are very peculiar, because the equation, the evolution equation for the covariance matrix is completely deterministic, also in the stochastic case, in the case in which you are measuring the system. This is a peculiarity of Gaussian system and makes everything much more easy to work with. Okay, having said that, the other ingredient that I will need in order to have a thermodynamical description of this system is a new entropic function. I will not use in the following the von Neumann entropy. I could do it starting from the collisional model, but I will not, and I will use another entropic measure that is the Wigner entropy. That is just the Shannon entropy of the Wigner function. And I will do this because the von Neumann entropy has some critical drawback, in particular when it comes to describing optomechanical system. As I said at the very beginning, the optical output mode, that is the one that we are going to monitor in an optomechanical system, is, for all practical purposes, a thermal buff at zero temperature. And it can be shown that using the von Neumann entropy to define the reversible entropy production, even for systems without the measurement involved, gives divergences whenever you are considering thermal buff at zero temperature. So that is problematic. It cannot be used for describing, for example, an optomechanical experiment. So as I said, in the following, we use this Wigner entropy, which first of all correspond to the Rényi-2 entropy for Gaussian states. And we know from the literature the Rényi-2 entropy have important thermodynamical consequences. The Wigner entropy doesn't give any divergence for t equal to 0 thermal bath, so I can use it also for describing a system in which I'm doing an homodyne on the output field of a cavity. And finally, this quantity converges to the von Neumann entropy and the thermodynamic entropy in the limit of high temperatures. So it has a well-defined thermodynamic high temperature limit, classical limit. Okay, having said that, I'm finally ready to speak about thermodynamics. And here I will confront two different approaches to a thermodynamic of continuously monitored Gaussian system. The first one, you can see the details here in this Nature Quantum Information of last year. That is the first work that we did on these systems. And in this work, we use a phase space approach to define the entropy production, the reversible entropy production. And in a nutshell, this can be done by looking at the dynamics of the system in phase space as described by a stochastic Fokker-Planck equation. So here, the green box is the standard Fokker-Planck equation, just written as a sort of continuity equation for probability currents. In the stochastic case, in the case in which you are measuring the system, there will be also a stochastic term. And starting from this evolution, one can rewrite the differential of the entropy, of the Wigner entropy, and identify in an ambiguous way the entropy production and entropy flux rates that appear in this expression. And these will be stochastic variables. Pay attention, this ds over dt is not stochastic because of the peculiarity of Gaussian system, because the entropy essentially depends only on the covariance matrix. However, this quantity here, the entropy production rate and flux, are in principle stochastic. So in order to obtain the information that we want, we need to take the average of this quantity over all possible realization of the stochastic process. And in doing this, one can see immediately that, now I will not explain what are all these matrices and stuff, don't worry, I want just to arrive to the concept. And the concept here is that by using a phase space method, again, I'm not going to do the detail of this, it's just enough to know that this quantity can be identified just starting from the stochastic Fokker-Planck equation, and essentially identifying what are the quadratic term in the currents that give you the reversible entropy production and the linear one that give you the entropy flux rates. And taking the average of this stochastic quantity, it can be shown, first of all, that the average entropy flux rate of the conditional dynamics is equal to the flux rate of the unconditional dynamics, which, if you remember, was something that I was assuming before in the collisional model, was holding only for particular class of measurement of the ancilla. Here, with the phase space method, it comes out automatically. And finally, one can recover the expression for the reversible entropy production, taking the average, and again, obtaining that this can be written as the unconditional one, plus an information rate, which now with an abuse of notation I'm writing like this, it seems, again, the mutual information before, but again, this is essentially the Holevo information rate, apart from a sign. So this is a phase-space semi-classical description that leads us to the same conclusion as before, to the same connection between informational quantities and thermodynamical quantities. And now I would like to show you what changes with the collisional framework. The results are more or less the same. Here, there are a lot of expressions. I don't want to focus on all of them, of course. But again, it's easy to rewrite everything in terms of just the covariance matrix of the system. And the collisional framework allows you to have all these very direct expressions. So for this is very advantageous. And finally, we can see the expression for the entropy rate and the reversible entropy production rate. Now, these A and D that you see here are the drift and diffusion matrix that were in the dynamical equation. But here you see that you have also these CY and CX matrices around. Now, these matrices are just coming from the interaction between the system and the ancilla. And the point is that all the quantity that have a Y are referred to the ancilla, while all the quantity with an X are referred to the system. So you see already that while in the semi-classical picture, I just needed the reduced dynamics of the system in order to get all my thermodynamical quantities, in the collisional model framework, this is not the case. I need information also on the state of the ancilla and the evolution of the state of the ancilla. Now, it's possible to bridge the two descriptions, in particular, if all the matrices that you see here, these C matrices, are invertible, it's possible to show that this expression can be written just in terms of quantity that are characterizing the reduced dynamic of the system, but this is in general not the case. So here there is an important point that can be seen with the collisional model framework. While the master equation or the stochastic master equation gives you a perfectly fine definition and description of the dynamics of the system, in general, it is not enough to characterize the thermodynamics. There are cases in which a consistent thermodynamical characterization can be done only by knowing further information about the state of the ancilla and so the state of the environment, apart from the one that is encoded already in an open quantum system master equation. So I think that this is an interesting point. And to conclude, since I'm also running a bit late, I will just show you some nice picture of an experiment that has been performed by the Copenhagen group of Professor Slisser, in which all these features can actually be found. Not seen, because I will not show you all the features, but they can be found all in that work. In that work, what they were using as a system was just a membrane inside of an optical cavity, the optical cavity being pumped by the usual laser, and the output mode was measured by an homodyne detection, continuously measured. The stochastic master equation of the system after an adiabatic elimination of the cavity mode was written in this form, where you see that there is a thermal bath, that is the phononic bath, Brownian motion. Then there was a quantum back action term coming from essentially measuring measuring the optical mode. And of course, there is a stochastic term that takes into account the conditioning on the outcome of the measurement. Now, for this system, again, the dynamics can be rewritten in terms of the first and the second momenta. However, here I will not show this, so just believe me, but you can find it in this physical review letter. However, this is exactly a case in which only the master equation of the adiabatically eliminated in the adiabatic limit is not enough to give you a consistent thermodynamical description. If you were to use the semi-classical approach that I was discussing before, you will obtain, in a brute force way, you will obtain inconsistencies, thermodynamic inconsistency, because you will not be able to take into account properly the heat fluxes, and you will get a result that is not correct for the entropy production. If I remember well, in that case, you obtain even a violation of the second law. The collisional model allows to have a correct interpretation of all the quantities, so to find the right thermodynamical quantities, even if in our work here we didn't use explicitly the collisional model framework, but we had to start from the master equation of the full system before the adiabatic elimination in order to get a consistent picture. In that case, we were lucky that the full master equation was still enabling a consistent thermodynamical picture, because it was exactly a case in which all the matrices that I was discussing before were invertible. But if you are given only the reduced dynamics, this is exactly a case in which you will not be able to get a consistent thermodynamical picture, even if you have the whole dynamics of the system is perfectly under control. And to conclude here, there are the results of the experiment, essentially. Here you can see various stochastic trajectories. So these are the, respectively, the entropy flux rate and the entropy production rate for different stochastic realization of the measurement, and the dark curve are just the average values. And in the figure here, instead, on the bottom right, you can see all the informational quantities. And it's interesting here to see that, again, here there is your information rate that is going to zero asymptotically, but you see that the differential information gain and loss are different from zero. So essentially here we arrive at an informational steady state. And this is kind of nice, because what is happening here, if you see actually in the previous slide, is that, so imagine the state as described in phase space by a circle. Here, this behavior is telling you that the circle in phase space is essentially shrinking. So essentially, by measuring the system, you are cooling it down. However, in order to keep it cooled, you need to continue to measure the system. If you interrupt the measurement, and this is what the informational steady state is telling us, if you stop the measurement, the system will start to heat up again to the initial state. So to the steady state of the unconditional dynamics, it is just a thermal state at a higher temperature. So with this, I have concluded. I hope that everything was more or less clear. What I have shown you is that we can, and we have extended a collisional model framework to continuously monitor its system. This has allowed us to define in a proper way the concept of informational steady state, and connect thermodynamical quantities with informational quantities with a very general formalism that can be applied to whatever quantum system you want to consider. In particular, I show you some application to simple qubit system that are prototype for, they can be prototype for more general applications, in particular because you can qubitize other interaction and simulate very general time continuous master equations. And finally, I have shown you both the advantages of the collisional framework when considering Gaussian quantum system, and the drawbacks. And the drawbacks were the one that I was discussing at the beginning, that in order to have everything, you need to know the correlation between system and environment and the changes in the environment, which is something that you usually don't have. In order to overcome that kind of drawbacks, you need to use the semi-classical approach whenever it is possible, which is not always the case. And finally, I have also shown you the first experimental verification of this infothermodynamic relation in a mesoscopic optomechanical system. With this, I stop speaking. Sorry for having been super long, and thank you very much for the attention.
Thank you very much for the interesting talk. So we have a few minutes for questions. So if you have questions, just you can simply unmute yourself and directly ask Alessio.
Hi.
Hi.
Thank you very much for the talk. I'm trying to understand this continuous measurement for the Gaussian systems. So do you learn like one of the quadruplets? Do you learn like Q or P, or can you in fact learn both approximately? And I guess also, like, when you're learning them, like, does it just look like diffusion as well in the on the Wigner state?
Yes, essentially. Well, it depends what you're doing now, because as I said, the measurement is encoded in this kind of matrices, which in the end are just a filter. So depending on if you're doing an homodyne in the position, or an homodyne in the momentum, or an heterodyne measurement, or a general dyne, you are learning different stuff. And these metrics here are essentially filtering, are connecting the first momenta that are both X and P with what you actually extract as an outcome. So there is a direct relation between the outcome, so the classical outcome that you will see in the machine, and the first momenta. And this relation is essentially a stochastic one. So in phase space, what you will observe, now I don't have a nice picture probably here, but you will see, oh no, wait, a couple of slides. What you will see in phase space is more or less always similar. You will see let's say that you start from this big circle that is your initial thermal state, centering in the origin. Then at each realization of your process, so for each different measurement that you're going to do, you will see the state that is in a different position in phase space, and you will see always the same evolution for essentially the circle. The circle will shrink always in the same way. It can also change shape, of course, because one is the deterministic evolution of the density of the covariance matrix, and the other one is the stochastic evolution of the first momenta. But what you learn depends on the kind of measurement, and indeed also the thermodynamical quantities, the entropy production, depends strongly on the type of the measurement that you are doing. I don't know if I answered your question.
Yeah, that's really helpful. Thanks.
Are there any other questions?
Oh. Hi, Alessio. Hi. How are you doing?
Hi, yeah. Fine, thanks.
Yeah.
You?
Hi. Yeah, not bad. I should confess that I am two timing, so there is another, group meet, administrative physics meeting going on. So I heard your talk like half some of the things, but it's still very interesting topic. So I was just wondering that so in the case of when you talk about collisions in the continuous variable case, are you really again using some Hamiltonian there to do the collision, like the swap Hamiltonian?
Yes, it depends on the case. I didn't show in our paper. We have also an example in which we define different kind of Hamiltonians. So, for example, you can have the XX interaction, or you can have some other PP interaction or whatever.
Right.
In the case of the experiment that I was speaking, then there was the interaction that was I don't remember which one. Probably was a position interaction.
Okay.
Essentially between the system and the ancilla. Just that the ancilla in this case is another Gaussian mode, or even composite one. So you can have n Gaussian mode as a system, m Gaussian modes as the ancilla, and then you describe them through an interaction Hamiltonian that essentially is the one that is here. This HS in general is an n plus m times n plus m matrix, and the off diagonal blocks are the interaction. Right.
Okay. I understand. Right. And one very general question. I don't know whether you really stressed this before at some point. I might have missed, but this is the broadest question. So what is the main difference? So when you have an informational steady state, right, is that So it need not still be the like the rho dot steady state, you know, so that how we define the density matrix steady state. What is the difference? So
is essentially that one. In the sense, it's a bit more. For example, for Gaussian state, for Gaussian system, when you have when you have your conditional dynamics, essentially the steady state here. The steady state here will come from. Okay. The steady state here you can define is as the one that has sigma dot equal to 0.
Yeah.
But that one will still change in time because it will still go around in phase space, no? So because the first momentum will still go around. So for stochastic system is not trivial, but is exactly the same thing. The steady state is the one that has sigma dot equal to 0. So it's exactly the same thing for Gaussian system. Is the usual steady state, is the one that you reach at late time. Just that, well, calling it informational steady state is just because we have this balance between this informational quantity that we are able to describe. And also because, again, as you know, if you cool down by measuring the system, you stop measuring, the system will eat up again. So if you stop acquiring information, the steady state will go back to the one of the unconditional dynamics. So you will lose the steady state essentially. But essentially, yes, it's the one that you have by imposing rho dot equal to 0. It's the same stuff. So it's not a new steady state. Right. It's just that we can characterize it from the information point of view.
So steady states for systems which may be driven but also monitored is the same as the informational steady state.
Is the rho dot equal to 0 essentially?
Okay, and it goes both ways, like they are like equivalent, or one is a subset?
It's exactly the same concept. The only difference is that well, there is no difference. The only point is that we can characterize the informational balance with the informational quantity that we have introduced. So that's why we call it informational steady state.
Okay, thank you.
You're welcome.
Maybe I just ask a small question. So here, would something interesting happen if you would add nonlinearity to, let's say, instead, so you would activate first, second, third, and also higher order moments. So in terms of, would something interesting happen to this balance between, so can you maybe extract something interesting in, let's say, the transition to a steady state with nonlinearity? Is there something interesting to be learned there? Or is it something, it would be very much similar here?
It's an interesting question. I don't know, I should think about it. I don't know what you can extract, what you can extract from that. In a certain sense, the situation will be similar because, for example, in the previous example of the qubits, there was also there an informational steady state. And in the case of qubit, you are clearly not playing with Gaussian system, Gaussian states. So the situation will be similar. There will be always the balance. The point is that, as you were pointing at, the informational quantity will be different, and so also the thermodynamics will be different. Then I don't know if you can use that as a witness of non-Gaussianity. But maybe yes, maybe you can use something like that as a sort of a witness of non-Gaussian correction. I should think about it.
Okay. Now, so if there are no more questions, let's maybe. So I'll thank in the name of everyone. So I'll clap. So thank you very much for this talk and also for the Q&A part.
Thank you very much for the invitation.
And thanks also everyone for joining us today for the talk. Okay, this is formally over. We can now stop recording.